This yesterday, and we went through how we graph polar coordinates, that we get a radius and an angle, and I said it's easier to turn to that angle and then figure out how far you go based on whatever the radius is. Notice that on this one we turn to an angle of 5 pi fourths, so we point in this direction right here, but the radius is negative, so the negative means you go in the exact opposite direction, 180 degrees or pi units away, and then we go 2 units in this particular case. So those negative radiuses or negative radii are important. We drew a couple fairly easy sketches. On this one, the only condition is that the radius has to be 1 or 2 or 3. So we get concentric circles there. And on this one right here, it only says that the angle has to be pi fourths. So you turn to pi fourths and you go forever in this direction and forever in the opposite direction. So it's kind of a funky way to define a line, but that's what it is. And then we went to more interesting graphs, something like this. And the way we did this is we made a theta r chart. It's easier to plug in the angle and then figure out the radius, just like it's easier to figure out what direction you're pointing and then figure out how far you go. We picked a couple points and we figured out that what happens here is we end up with a circle that kind of goes around by the time we get to pi, or 300 or 180 degrees, and then it just continues to go around and around and around. So we just get this little circle here. Then we had one that was a little bit more interesting. We got about halfway through this, but you'll notice we started out with a radius of 0. Okay, got to a radius of 2.6. So started out when we were pointing at 0, the radius was 0. When we were pointing at pi 6, the radius is 2.6. When we're pointing at pi fourths or 45 degrees, it's 3. So we're pointing here, and as the angle gets bigger, the radius gets bigger. So we come out like this. And then it starts to get smaller. So by the time we're pointing up here at pi halves at 90 degrees, we're right back to 0. And then we graph this stuff where the angles would be in quadrant 2, but every one of the radiuses were negative. So what ended up happening is we had this little petal, and that's what it's called, that looks like this. So I'm going to come back here, and I'm going to retrace this. Now, we've only gone from 0 to pi. That's what we did yesterday. So if I go from 0 to pi, I get this piece. Then I get this piece. Where do you think I go next? Third quadrant. We get something like this. It's the same type of shape, same petal, it ends up there. Now, you have to be careful about this, but because of the pattern that we were just talking about, if I plugged in, this would be 225 degrees, or that would be 5 pi fourths. If I plugged in 5 pi fourths into this, that would be 3 times the sine of, well, that would be 10 pi fourths, which we could reduce, right? So we'd reduce that. That would be 5 pi halves. So this would be 3 times the sine of 5 pi halves. So let's think about where 5 pi halves is. 5 pi halves would be all the way around here. And what's the sine right there? It's 1. So if I multiplied that by 3, I end up with 3. So if I'm pointing at 5 pi fourths, I do end up with this point right here, just like I'd suspect. So we went around like this. So let's just carefully watch the pattern here. Go around and make this petal, go around and make this petal, then this petal, and then the last one would be over here. So go something like that. And then if I kept going around the circle, if I plugged in larger and larger angles, I just keep going around and around and around. Okay? So this is called a rose. It happens to be a 4-leaf rose. Okay, or a 4-petal rose, and each one of these is called a petal. Now, this is an absolute pain in the butt to graph these this way. Okay, this is plotting points. This isn't really understanding how the shape makes the shape that it does and all that sort of stuff. So we're going to change this a little bit, and we're going to build on some of the graphing skills that we learned in 1010, 1050, and really the ones that we worked on in chapter 3, where we were, or actually it was chapter 2, where we were graphing all of the trig functions and their transformations. So we're going to graph that same one. Okay, so this is example 7. I made this example 7 star. We're going to graph it not by making an XY table, but we're going to think about, well, if I actually graph this on a coordinate plane, like an XY plane, rather than graphing it on the polar plane, let's take a look at that and figure out what that would look like. So this is just a sine function. What's the amplitude of the sine function? Amplitude is 3. We know how to draw a sine function with an amplitude of 3. What does that 2 do to the sine function? Okay, I heard a couple things. I heard somebody say it speeds it up, which changes the period. So if I multiply theta by 2, what's the new period? The new period is pi. Okay, so the new period is pi. So that means it's going to make the sine graph, let's see, like this. There's one cycle, right? And there's another cycle. So it's going to make 2 cycles as it goes from 0 to 2 pi. Everybody remember that? That's not hard to do, right? Okay. I'm going to come back here and I'm going to graph this again, and I'm going to do this in different colors. So the first one I'm going to do in black. So this one right here, all of those are in quadrant 1, because this is pi halves right here. All of these are in quadrant 2, because I go between pi halves and pi. In this quadrant, I'd be going in between pi and 3 pi halves. So it looks like this. Oops, grab a different color. Okay. And then in this last quadrant, it looks like that. So does everybody agree that these angles are all in quadrant 1? They're between 0 and pi. These are all between pi halves and pi, so that's going to be quadrant 2, quadrant 3, and quadrant 4. Is everybody good with that? Okay, let's draw what happens in quadrant 2. Let's look at this and figure out what goes on. Okay, this is the angle we turn to. That's what this axis represents. Angle we turn to, or I suppose if you're an English major, to which we turn. Okay, and this right here, this is the radius. This is how far we go in that direction. So if I take this point right here, what angle do I turn to? 0. How far do I go? 0. Right here at the pole. What angle is this? Pi fourths. How far do I go? I go 3 units. So I'm going to point to pi fourths and I'm going to go 3 units. Now, it didn't go straight out there, did it? It gradually got bigger. Notice how this gradually gets bigger? So if I pointed to like 10 degrees or something like that, it's going to gradually get larger and larger and larger, and it's going to go like this. Now, if you can figure out what this part of the graph right here does, between 0 and pi fourths, what does it do between pi fourths and pi halves? Okay, it goes out and it basically comes back, right? So it's going to swing out here and then it's going to come back. Good there? Okay, and I'm going to fatten that up just a little bit. Okay, let's take a look at this one. If I pointed to pi halves, how far do I go? 0. Okay, so again, we're right back here at the pole. What angle is this? 3 pi fourths, 135 degrees, right? So we're going to point over in this direction. What's the radius? Radius is -3. So even though I'm pointing in this direction, where do I actually graph the point? In the 4th quadrant. So I'm pointing in quadrant 2, but I actually graph this point in quadrant 4. Why do I graph it in quadrant 4? Because all of those radiuses are negative. Now think about this. If I know what shape this made, what shape does this make? The exact same shape. Look at the symmetry there. So it's going to swing out here, hit this point, and swing back. Now let's deal with this one right here. What's this angle? 5 pi fourths. Okay. So we're pointing at 5 pi fourths. How far do I go in that direction? I go 3 units. The radius there is positive, so not only do I point in that direction, that's actually where I graph the points. So I'm going to swing out here, hit 3 by the time I get to 5 pi fourths, and then, so that's this swinging out there, and then I swing right back in the same fashion, so it looks like this. Now, this last one is in green in quadrant 4. I actually graph in quadrant 2 because all of these radiuses are negative. So that's why I get this one right here. So if I had to graph this point, if I had to label that point is actually 7 pi fourths. Okay, that's the angle that we turn to. And then the radius is -3, right? Again, that's convention. We write the radius first, then the angle, but it's easier and in fact better to think of the angle and then the radius. Everybody good there? The angle 7 pi fourths, it's over here, but because the radius is negative, we actually graph it in quadrant 2. Okay, are there any questions? Okay, would you label this point right here? That one's not tricky. We're not trying to trick you there, because remember, the radius there was positive. This is going to be 3, 5 pi fourths. Okay, if this were a test and you said it's 5 pi fourths, 3, I'd take that. We'd be okay with that. Okay, are there any questions there? Okay, what I'd like you to do is I'd like you to take a look and compare. Look at all the scribbling and all the work we had to do just to produce 2 of these little petals right here. And look at how little work we did in order to produce this right here. Okay? Here's why this works the way it does. This graph over here is a picture of every possible point you can put in a theta r table. It's every single one of them, and you don't have to know exactly what the points are. You just have to hit the key points. The fact that it starts at 0 and gets up here to 3. Down here to 0 again. Here it's -3 at 3 pi fourths. And things like that. Okay, now if you need to know an exact value somewhere, like let's say, I'd really like to know what that is right there. We'll plug in pi eighths and figure out what it is. Okay? But there's not a need for a bunch of precision here. We need to have the general shape and be able to label a couple key points on this. Not all of them. You don't have to make a whole table of points there. You just need to have some key points there and have the correct general shape. Okay, are there any questions? Okay, so that's the technique we're going to use. We're going to use this graphing method in order to do these. And the cool part about this is this should go relatively quickly, and we should see a relationship between the graph that we make in Cartesian form, so in like an xy plane, and the one that we get on the xy or the polar plane right here. So let's think about this. I want to graph r equals 1 minus sine theta. What does the 1 do to the graph? Moves it up 1. Now this isn't typically how we write this, so I'm going to rewrite this as negative sine of theta plus 1. So that moves it up 1. What does the negative in front of the sine do? Flips it upside down, right? So I have a new center line for this. Have I changed the amplitude or anything? Nope. Okay, remember it starts on the center line, it starts on the midline. Haven't changed the amplitude, haven't changed the period. So I'm just going to go through and graph the 5 key points that we learned in chapter 2. So it starts right here, drops down to here, back to the midline, up to here, and to there. So the graph looks something like this. Goes down to here, up to here, up to here, and to here. With me? Okay. And before I forget, if you want polar graphs that look like this, I've got some on the website. So if you just go to the chapter 6, there's polar graphs there. I think there are 4 of them that are a little bigger than this that fit on one page. It's pretty tough to graph polar curves if you don't have a decent piece of graph paper. Okay. All right. Any questions there? Okay. So let's graph this. Notice that this was, so let me label this. This is 0. This is 2 pi. This is pi halves, and this is 3 pi halves. And finding or estimating any point in between there actually wouldn't be too bad. So let's label these 5 key points to start out with. So on this first one, okay, what angle do I turn to? 0. How far do I go? I go 1 unit. So I'm pointing at 0, I go 1 unit. There's my point right there. Okay, now, by the time I get to pi halves, I turn to pi halves, what's the radius? 0. Radius would be 0. Okay, now my question for you is, did it go like this? Straight there. It didn't. Okay, and you can check this in between, and this is where estimating comes in handy. This would be about pi fourths. We could figure out the exact value of that number, but it's a fairly small number. It's maybe a half or a fourth or a third or something around that. And you can look at it and you can estimate what it is. So if I point to pi fourths, how far do I need to go? About a half, roughly a half. Is everybody okay with that? So if I put that one extra point there, pi fourths, and I'm going to go a half, here's what I've got. I don't have a shape that went straight from this point to this point. It acknowledges that I started out with a radius of 1, and the more I turned, the smaller it got. So it looks like this. Okay. By the time I got to pi, what's the radius? Radius is 1. Did it go straight here? It didn't. It didn't go straight there. So let's pick a point. Let's find one about right here. So that would be about 3 pi fourths. See how easy it is to look at the graph and estimate where it would be? And roughly, what is the radius when we point to an angle of 3 pi fourths? The same thing, right? So whatever you guessed it was over here, if you guessed a half, we better guess a half over here. So if I point to 3 pi fourths, I'm going to go out about a half a unit. So it started out at 0, but it gradually got bigger. By the time I get to 3 pi halves, what's the radius? Radius is 2. So if I'm pointing at 3 pi halves, I go out to 2. Now, it didn't do this. It did not go straight here. And I'm sorry if you're getting irritated, but every time I get a test on one of these, somebody does a graph that looks like this. That's not what it looks like. You don't fundamentally understand what's going on here if you draw a graph like that. So what happened here is it gradually went from a radius of 1 to a radius of 2. So it must have gradually gotten bigger, not gone straight there. If you want to take a guess, 5 pi fourths, I'd say it's about 1.5, 1.6 or something like that. So we'd be out about right here. So it's going to look something like this. Now the cool part about this is once I get to here, it's a no-brainer as to what the rest of this looks like, right? Starts with a radius of 2 and then gradually gets smaller to a radius of 1. So we'd swing around and do something like that, okay? So what does this look like? Looks like a heart, and it's called a cardioid. What? Did I spell it wrong?
No.
Okay.
It's called a cardioid.
Yeah. It's somehow mathematically poetic. Okay? What I want you to look at here is let's notice a couple things about this. You'll notice that when we started off with a radius of 1, it shrunk down to a radius of 0 and then got big again. Started out at 1, shrunk down to 0, and then got big again. Went from a radius of 1 all the way out to a radius of 2 and then shrunk again. So it went like this. Okay? We don't have any petals here. We just have this funky heart-shaped thing called a cardioid. Okay? What is the largest radius? 2. Where does it occur? 3 pi halves. The largest radius is 2, and it occurs at 3 pi halves. Okay? Good thing to keep track of. Let's take a look at the next one. Now, this one's different. Okay, we've got 1 minus 2 cosine theta. What did the 1 do to the graph? Moved it up. What does the minus 2 do? 2 things. It's a vertical flip, right? Okay, and it changes the amplitude. What about the period? Doesn't change the period at all. So I have a new midline. We're going to move it up here. But it starts at, well, let's see, we flipped it upside down. So it's here, 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 and here. And then if I stick with those colors, it goes like this, then like this, then like this, and then like this. And we can see that there's some symmetry in each one of the quadrants. Like this is going to be quadrant 1. This is what happens in quadrant 2. This is what happens in quadrant 3. And this is what happens in quadrant 4. And we can see there's got to be some symmetry among those quadrants. So let's take a look and see what we get when we graph this. What is this point? Where do I turn to and how far do I go? Point towards 0, radius is -1. So I'm pointing towards 0, but the radius is -1. So I actually graph a point over here. By the time I get to, and let me label these, so we've got 0, pi halves, pi, 3 pi halves, and 2 pi. By the time I get to pi halves, what's the radius? 1. Okay, watch. Did it go straight from here to here? It didn't. In fact, something really interesting happened somewhere in between there. Yeah.
It became positive before it reached pi halves. That's weird.
It is a little bit weird. Okay, so here's what happened. About right here, and we can just estimate, about right there, the radius is 0, right? So I'd say that's about pi thirds, 60 degrees-ish. So did it go straight to here and then up? Did it make an L shape? It didn't. Because about right here at about pi fourths, the radius is negative. So if I point at pi fourths, I've got a little tiny negative radius. So it did something like this. Went around like this. It still didn't go straight here. It gradually got bigger, so it looks something like this. Any questions? So we start out at pi halves with a radius of 1. What happens by the time we get to pi? Radius is 3. So all the way out here. And it gradually got bigger. I'm going to pick a point in between, let's say 3 pi fourths. Let's figure out roughly, just approximate, how big would that radius be? If I turn to an angle of 3 pi fourths, how far do I go? About 2.5. So let's point over here and let's go 2.5. So it gradually got bigger like this. Came out here, ends up like that. Now, we've graphed this black piece and this red piece. What do you notice about the rest of this, the blue and the green? It's gonna do exactly the same thing. So it started out negative, got to 0, and then went positive, got all the way to 3. Now it's going to do the same thing in the opposite direction. So by the time we get to 3 pi halves, what's the radius? 1. So it did something like this. Swings around down here like that. It hit 0 somewhere. I'd say that's about, well, if we did this in degrees, maybe about 300 degrees. That's going to be 5 pi thirds, roughly. So it's going to get smaller like that. And this little piece right here, pay close attention to this. Even though we're pointing at quadrant 4, where am I actually going to graph this piece right here? In quadrant 2, because the radius is negative, right? So we're going to get a shape that looks something like this. Okay? So it started out here, went around like this, and around there. Okay, are there any questions?
What's this called?
This one has a name, yeah.
You got like 2 different points on the black part. How did you get the second point?
This one right here.
No, you got the negative one and then the one that goes up and the one that goes to the left. How did you get the second one?
Okay, let me make sure. So this one here,
Yeah.
this one here, and that one there, right? Those are the 3 that we did on the black part.
Yeah.
Okay, so that's this one, and this one. So turn to an angle of 0, go -1 unit in that direction. So we point over here, but because it's negative, we actually graph it over here. At about, well, let's see. Whoops. What are we here? That's the pole right there. So at about 60 degrees, we hit 0. And then by the time we get to 90 degrees, or pi halves, we end up with 1. If you wanted to check a point in between, like let's say pi 6 right there, that would be about -1/2, so that's this one that I graphed right there. Is that all right? Okay. What is the maximum radius? 3. Where does it occur? At pi, right? Right here. Okay. This one is called a lemmason, and it's got one of those accents on it. It's called a lemmason. This happens to be a lemmason with an inner loop. and let's do a couple more. Okay, any questions? Okay, once we get this down, we can make some really cool shapes. Let's take a look at this one here. What happened with the 4? Changes the amplitude. What does the 2 do? Changes the period. So this is going to be twice as many cycles. Okay, and going to have a larger amplitude. So I'm going to mark this off like this, and I'm going to do 0, and I'm going to do this one in degrees, 0 and 360. So this is going to be 180, that's going to be 90, and that's going to be 270. And it needs to finish a cycle in half the time. So it's going to finish a cycle in 180 degrees. So it's going to start up here at 4. It's going to end up here, and it's going to go something like this. And notice that by putting these points on here, those are a bunch of points we're going to graph. And then it does the same thing again. Okay, where do I point? For this one here. 0. How far do we go? Okay, this goes 4. And how far down would we go? We'd go to -4. So we're going to point at 0, and we're going to go out to 4. Okay, what's this point right here? If that's 90, this has got to be 45. So the radius at 45 is 0. Again, it didn't go straight here. It gradually got smaller and went like this. So let's do this piece right here. Between 45 degrees and this would be 135 degrees. So even though I'm pointing between 45 degrees and 135 degrees, where do I actually graph this? This would be 90 and -4, right? So that would be down here. So it's going to do like this. Between 135 and what would this one be? 225. At 180 degrees, the radius is 4. So I'd be out here. Swing back around. That takes care of this one here at 315 degrees. Well, no, it doesn't. It does that one right there. Then between 225 and 315, so this is 225 and 315. Even though we're pointing in this direction right here, where do we actually draw this? In the exact opposite direction. So it's going to come around here like this. And then what does this little slice right here do? Finishes it off. Between 315 degrees, and notice what I'm pointing at when I come through this radius. So if I come around here on this petal right here, I'm pointing at 315 degrees, and then I finish it off like that. So if I were to color code these, that's this one. That's this one. This one is right here. This one's here. And then I come back and I finish this one off with that piece there. It is now. Okay. Any questions? Is that hard?
It's weird.
Well, wait just a minute. We'll do some really weird ones. They don't get any more difficult than that. Okay. I would like you to think about what something like this next one would look like. R equals theta. Well, if I were to graph that over here, so if this is my theta axis and this is the R axis, they're both the same, right? And this is another reason why it's important to think of this in terms of radians rather than just degrees, because it wouldn't make any sense to say the radius is 90 degrees or something, okay? But this is just a perfect 45. So if I went to pi halves, that means the radius is also pi halves. If I went to pi, that means the radius is pi. So if I point to 0, what's the radius? Radius would be 0. By the time I point to pi halves, the radius is pi halves, which is about 1.5. And again, it gradually got bigger. By the time I'm pointing to pi, the radius is 3.14. Again, it gradually got bigger. By the time I'm turning to 3 pi halves, it's about 4.7. So 4.7. So about right there. So what does this look like?
Spiral.
Looks like a spiral. By the time I go all the way around full circle, 2 pi, it's going to be 6.28. So that's going to be, let's see, 1, 2, 3, 4, 5, 6, about right there. So all this is going to do is it's going to continue getting bigger and bigger and bigger. It's going to be a big spiral. Okay, has a name. It's called the spiral of Archimedes. You don't need to know that, but that's what it would look like. Okay, what? Okay, and it's not as pretty as the other ones. Any questions? Okay, so you can make some really cool shapes in polar equations that you can't make in Cartesian or rectangular equations, but some of them are very similar. We've seen some lines and we've seen some circles and stuff like that. So one of the things you need to be able to do, and this is basically preparatory math so that you can figure out some stuff in Calc 2 or Calc 3. We need to be able to convert from polar to rectangular and rectangular to polar. So that's what we're going to practice right here. So let's see. We've got x squared plus y squared equals 9. Now, you just got out of 1050 last semester. Does anybody recognize this? It's a circle. Where's the center? The origin. And what's the radius? Radius is 3. Okay? Well, there were 4 equations that we can use to translate or convert from rectangular to polar and polar to rectangular. Okay? One of them was, let's see, it was x is equal to r cosine. You're going to need to know these for the test, by the way. Y is equal to r sine. Remember the other ones? R squared equals x squared plus y squared. It's just the Pythagorean theorem. And then the last one was the tangent of theta equals y over x. And you had to be a little bit careful with this because if you use a tangent inverse, it's only going to give you an angle between negative 90 and 90. So you got to be careful and make the adjustments off that. Are there any questions there? Okay, I would know those because on a problem like this, you've got to convert this into r's and thetas. So you've got to find stuff that looks familiar or looks like parts of this and then plug them in. Well, what we notice immediately is there's an x squared plus y squared. What does this say x squared plus y squared is? R squared. R squared equals 9. Go ahead and take the square root. Whether you use the plus or the minus doesn't really matter because it doesn't matter what the angle is. We're always going to go 3 units. 3 units away from the pole. Pole is the same as the origin, so isn't that the equation of a circle of radius 3 centered at the origin? It is. Okay? So which is easier? Rectangular or polar? In this case, polar is a lot easier. Anything that's kind of circular in nature or is better kept track of in terms of a direction and a distance, polar is going to be really useful for that. Okay, let's take a look at this one. Nice, easy line. I've got to change this into r's and thetas. Get rid of all the x's and y's, turn them into r's and thetas. So wherever there's a y, what can I put? I can put an r sine theta. Wherever there's an x, I can put an r cosine theta, and the minus 1 just stays the same. Now, technically, we've made the conversion. We've changed from rectangular form to polar form. Usually, you should solve for r. You should get r by itself. And in order to do that, we'd have to move this on the other side. So we'd have to do r sine theta minus 3r cosine theta equals negative 1. How do you get the r by itself? Factor it out. So you'd have r sine theta minus 3 cosine theta equals negative 1. And then finally, to get r by itself, we change colors so we don't confuse this. It would be r equals -1 divided by that stuff right there. So sine theta minus 3 cosine theta. And that would be the answer. Any questions? Which is better here, polar or rectangular? Rectangular by far, okay? It's also a little more familiar and that makes us feel good. Okay, let's convert from polar to rectangular. These were both given in rectangular form. We converted to polar. Now we need to be able to do the opposite. Take a good look at this. Again, if you're changing from polar to rectangular, you're getting rid of all the r's and thetas and you're replacing them with x's and y's. See anything that looks familiar? R cosine theta is the same as, there we go, x equals 2. It's that simple. This one's a little more tricky. You're right. How did you do that?
R squared is the same as r times r, so I put r cosine theta times r sine theta equals 4.
Okay, it would be a bad move to change this to x squared plus y squared right here. It would be much better to break this up and recognize that I can write that as r cosine theta and r sine theta. And then I've got two things that are recognizable rather than just one. This is an x and this is a y, so it's x times y equals 4. This one's kind of interesting. See anything that looks familiar there? If we're going to make a conversion, I've got to have an r cosine, an r sine, an r squared, something like that. This one doesn't have an r squared and it doesn't have an r over there. And if I tried to divide by r, that's not what I need. I need an r times the cosine of theta. I don't need it in the denominator. Any ideas? It's an equation. As long as you do the same thing to both sides of the equation, it's okay. Yeah. Multiply both sides by r. If I multiply both sides by r, I get r squared 2r cosine theta. And then I get something that I can substitute for here. This is x squared plus y squared. And over here I have 2x. Does anybody recognize this? If you moved this onto this side, completed the square with x and with y, y is already a perfect square. This is going to end up being a circle, okay? So you could do x squared, whoops, that's going to be a minus 2x plus y squared equals 0. Complete the square here, you'd add 1, so you'd add 1 here. So this is x minus 1 quantity squared plus y squared equals 1. This is a circle whose radius is 1 that's centered at 1, 0. Okay? Radius is 1, center is 1, 0. So it would look something like this. Center's right here. That's what it would look like. Any questions? Yeah.
So when you squared the r, how did it become 2r cosine?
I didn't square the r. I multiplied both sides by r. So I just took this side, multiplied by r here, and multiplied by r there. Didn't square it. Okay? Let me see. That's almost like this one right here. This one's centered at 2 and has a radius of 2. Very similar type setup to the problem that we just did. Okay? So it is a circle. Okay, are there any questions? Okay. You've got a couple problems on your assignment that are like this. I think there's either one or two, like example 14. I'll post an article on the website that explains how these work. But here's the basic idea. Dealing with r squared is a huge pain. Okay, so I need you to think about this for just a second. We're going to use that graphing technique that we talked about earlier, but we can't, wouldn't make any sense to have an r squared axis. Okay, that doesn't really make any sense. So what we're going to do for the time being is I'm going to take this and I'm going to change it. I'm just going to graph r equals 9 cosine 2 theta. Everybody good with that? We'll take care of the square in just a second. So that means I've got an amplitude of 9. And what's the period? Period's pi. I'm going to do this in degrees just to make it a little bit easier. So we're going to go 0, 360 degrees. Okay, in the center I'd have 180 degrees, and then I'll mark these. So again, sticking with that beginning, middle, and quarters and all that sort of stuff. And then I'm going to go up here to 9, and I've got to go all the way down here to -9. Any questions there? It's a cosine, so it starts up here, and it's got to complete a cycle this quickly, so here's what it looks like. Okay, I'm going to do this in a dotted fashion here. So it's going to come down, go like that, come back up. And finding points that are on this graph, labeling the 5 key points, that's not very hard, is it? Okay, so that's what it looks like, right? Okay, are there any questions? Okay, well, here's what I'm really after. If I'm going to graph r's over here, and it's r squared equals this stuff, I could figure out what r is, not by just ignoring the square, but by doing this. Let's take the square root. So that means take the square root of all of these values right here. So let's do this one. If I take the square root of 9, what do I get? I get 3. If I take the square root of 0, what do I get? I get 0, okay? So it pretty much looks like this. We could argue about this little tail end right here. It actually would have a little bit of a loop right there, but that's about what it looks like. Anybody have any issues with this right here? You can't take the square root of a negative, okay? So we get to ignore this. We're not going to take the square root of a negative. There's no point there, okay? If I take the square root of this, I get 3. So it looks something like this. And if I take the square root here, I get something like this. Is everybody okay with that? So I'm going to erase most of this, and I'm also going to come back here, and I'm going to color code this just a little bit. I'm going to make this red, and I'm going to make this blue, and I'm going to make this green. Good? What angle? 0. How far do I go? I go 3. So that's going to be 0, go out 3 units. What is this angle right here? 45 degrees, pi fourths. So that's going to be 0. And it didn't draw a straight line. It gradually got smaller, right? Okay, what happens in between 45 degrees and 135 degrees? Do I have any points to graph? Nothing. It just sits there. What happens in between 135 and this would be 225, right? Radius at 180 is 3. Starts out at 0 when I'm pointing toward 135, and then it ends up at 0 again by the time I get to 225, so it's going to look like this. And then what happens in between 225 and 315? Nothing. We just sit there, okay? And then we get this little piece right here. And what do you think this little piece does? Finishes that off right there, okay? Now, what I'd like you to think about here for just a second is, see how it starts at 0, gets big, and then gets small? This is a little petal. This is that entire petal right here. This is half a petal. That's the other half of the petal. Now, this is the whole graph. We're going to look at that a little bit more closely in just a second, but I want you to take a look at this one right here. What happens from here to here? From about 60 degrees to about 300 degrees. It starts off at 0, gets big, and then gets small again. This is like a big petal, it's just not symmetric. Goes like this. And then this is the start of a small petal inside here, and that's the end of it right there. Okay? Any questions there? Okay. Now, one last thing, and then tomorrow I'm going to finish up. We'll look at some interesting graphs from this. This is enough information that you can finish the entire section. I do want you to consider this. Was this square root in the problem to begin with? Nope. Okay, so technically, when you take the square root of something, what do you have to put in there? You have to put a plus or minus. So technically there would be this, this, and this. And I'll show you on the calculator how you can make your calculator graph these. Okay, and I'll show you that it actually does do this piece along with a piece that's in the exact opposite quadrant. So if I'm graphing this piece here, what would this one graph? Same piece over there in the exact opposite direction. Okay, so we'll take a look at that tomorrow. Okay, that's enough. You can get started on 6.4. Office hours tomorrow, quick quiz, and we'll just talk about some details on this section.